I'm Matthew.
I'm Michelle.
I'm Minnie.
I'm Paige.
I'm Denise.
I'm Dan.
I'm Sarah.
And I'm Jessica.
I'm Dan Fleesick. I'm a physicist working for the U.S. Navy at the Naval Surface Warfare Center in Panama City, Florida. So in this episode of Sci Notes, we'll be doing some exciting experiments and having some fun with chemistry. We'll start by exploring density and how materials with different densities interact. Then we'll experiment with chemical solutions and change pennies into silver and gold. Next, we'll create a cold lava lamp using, get this, Alka-Seltzer. Then we'll experiment with some very toxic solutions to create beautiful golden rain. And to top it all off, we'll combine rust and aluminum powders to produce a chemical reaction that will look like the 4th of July. Stay tuned for Sci Notes, Chemistry. We'll begin this segment by talking about density. Density is basically the amount of stuff in an object. It's the object's mass, the amount of matter in that object, divided by its volume, how much space it takes up. Here's an example of density. Take a large room and put 50 people into it. Looks pretty crowded, right? Now take the same size room and put just 5 people in it. The room with only 5 people in it is 10 times less dense than the same room with 50 people in it. The room's volume didn't change, but its mass did. So as you can see, density gives us a way to understand the relationship between mass and volume. So to further visualize density and see how substances with different densities interact with one another, we'll construct a density column. It's a container with several layers of liquids that don't mix, and they'll settle out based on their relative densities. This is a project you can actually do right at home with the proper materials. There are many different ways to make a density column. This version has 3 layers and is actually shakeable. Once you allow it to settle, the layers will always return to their proper position. This is an interactive experiment you can easily do at home. Just be sure to be safe and ask your parents if you need some help handling some of the substances. And if you don't have the materials on hand, just write them down so the next time you're at the grocery store, you can pick them up for your experiment. While working in the lab, it's important to always wear personal protective equipment, or PPE. The 3 main pieces of gear that we need are a lab coat, our gloves, and goggles. A lab coat protects your clothes. Gloves protect your skin. And it also depends on what you're doing, because I'm using chemistry gloves here, but you can also use these big gloves for heat protection if you're doing something hot. And then finally, goggles protect your eyes. Goggles are the most important to have because your eyes are very delicate and sensitive to lots of different chemicals. Here's how PPE can save your life in the lab. Here are all the materials that you'll need for our density column. Water. I'm using distilled water, but any kind of water works. Vegetable oil, rubbing alcohol. I've got official lab grade rubbing alcohol. You can buy 91% or 60% in the stores. The higher concentration, the better. 91's the best, but if you can only find 60% or lower, that's fine. You might just have to use a little bit more alcohol. Salt, food coloring, and some kind of a sealable jar. Let's begin the experiment by adding equal amounts of each liquid to the jar. We don't have to be too exact here, so it's okay if they aren't perfectly equal. It is important, though, to pour each layer carefully and slowly. So first we'll do the water. Next is the oil. And finally the alcohol. And I'm going to be extra careful when I pour this one, just to make sure it goes on top. So now you see we have 3 layers. These layers form because each liquid has a different density. The water is the most dense, so it sinks down to the bottom. The oil is less dense than the water and floats on top of it, so it sits right up here. The alcohol is the least dense of the 3, and it doesn't mix with the oil, so it floats on top of the oil. So let's add some food coloring so it looks a little bit nicer, and then we'll have to shake it to mix the color in. Feel free to choose your favorite colors or even combine multiple colors to get a nice mixture here. And now we just have to wait for it to settle back out. So it looks like everything's settled out, but wait a minute, now there's only 2 layers. So there's the oil is definitely on top, this yellow liquid, and the watery layer is on the bottom, the blue. There's a little bit of a cloudiness in the middle, but that's just the 2 layers, they're still disengaging, they're still separating. So there's definitely only 2 layers. And plus, before, we had the third layer was on top of the oil, and that's definitely gone. So what happened? Well, when we shook the jar, we actually disturbed the layering, and the top and the bottom layers combined into one, since the alcohol, which was on top, and the water, which was on bottom, they can mix together, and the oil was the only thing separating them. So it turns out we can actually fix this with a neat chemistry trick called salting out. Salting out is when we add salt to our mixture, which forces the mixture to separate. You can think of it like the salt is repelling one liquid and attracting another. So we need to add enough salt to saturate this bottom water layer. This means that no more salt can dissolve. And now we just need to dissolve the salt, and the easiest way to do that is to just shake it around again. And this will take a good minute or so of shaking to dissolve everything as much as you can. Okay, that should be enough shaking, so I'll just let it settle out again, and we'll see if we notice any changes. So now that you see the different layers forming and separating after some time left alone, you might be wondering why this happens. Well, the reason is something called polarity. So for our experiment here, water is very polar. And here's a little model of the water molecule. So we've got 2 white hydrogens and 1 red oxygen. So the electrons are actually attracted towards the oxygen atom and away from the hydrogen atoms, because the oxygen pulls more strongly than the hydrogen. So this means that this side of the molecule is negatively charged, and the hydrogen side is positively charged, so therefore very polar. Isopropyl alcohol, our rubbing alcohol, is actually slightly polar because it has this charge separation, but the positive charge is buried in the middle of the molecule. The 2 groups on the sides, they hide the positive charge from the rest of the world. So isopropanol has a bit less than half the polarity of water because of this. So oils, like our vegetable oil, are made of very long chains of carbon atoms, like this. So they're more or less symmetrical, and there really isn't anywhere that pulls electrons more than anywhere else. So this means that oils are non-polar. They don't have a charge because there's no charge separation at all. So as you can see, density and polarity are very interesting concepts that help explain how substances interact with each other or not at all. I hope that you were able to follow along with this experiment at home, but if you haven't already, pause the video and try it out. I bet you'll be able to find these materials in your kitchen or the next time you're out grocery shopping. Here's another fun density experiment that you can try at home. You'll need a big container and a few different types of soda. Make sure to get a diet soda too if you can find one. Once you've gathered all your materials, we'll start by filling your container with water, which I've already done. Now before we drop in the cans, since we're doing a scientific experiment here, let's make a hypothesis. What do you think will happen? Will they float or sink? So now let's drop the cans in. Mountain Dew, looks like that one sinks. Got regular Coke, and actually floats. And Diet Coke also floats. It looks like it floats a little bit higher actually. This all has to do with density. Each can is the same size, so the volume is the same, but they all have different ingredients, and so they have different masses. The culprit here is really the sugar. The Mountain Dew has the most sugar, which makes it the heaviest, and that's kind of unfortunate because that's my favorite. The regular Coke has a bit less sugar, so it's about the same density as water. It's a little bit less dense, so it bobs around sort of near the top. The Diet Coke has no sugar, so it's actually the lightest of the 3, and it'll float the highest. If your hypothesis was wrong, don't worry, because in science, being wrong is actually a good thing. Because that just means we can ask more questions, and we can do more experiments, and we can have a lot more fun. Yay! Before 1982, pennies were made up of solid copper. Since then, though, they've been actually made up of zinc with a thin copper coating. The reason they did this was because the price of copper started going up, and it actually cost more to make a penny than the penny was worth. An easy way to tell what kind of penny that you have is by looking closely at the head side to see the date. In this segment, we'll clean up some older, worn-out pennies and turn them into silver and gold using chemical reactions. Because of the toxic solutions we're using here, this isn't really an experiment that you can just do at home, so just follow along. Let's begin by cleaning several pennies by placing them in a table salt and vinegar bath for a few minutes until they're shiny. Over just a few minutes, the acidic, salty solution dissolves the tarnish on the pennies to reveal clean, shiny copper. So now let's remove the pennies and rinse them with distilled water. So now that we have clean pennies, we can create the zinc plating solution in a little petri dish here. We'll start with this solution of zinc chloride. And this is 1 molar. Molarity is a measure of concentration, so it just tells you how much zinc chloride is in here. And then we're going to need to add in some powdered zinc metal. So now that our zinc solution is made, let's place the petri dish here on over top of a heating source. So I've got a butane micro burner here, and we're going to use this burner to heat this until it just begins boiling. Once the solution just starts to boil, we'll immerse our pennies in the solution for about 30 to 60 seconds, just until they start to appear silver. What happens here is that this solution contains both zinc metal powder and zinc ions that are dissolved in the liquid. Zinc is a more reactive metal than copper is, and so it becomes chemically reduced, and it grows a thin, even plating of zinc metal on the copper's surface. And this layer of zinc is what makes the penny look silver. So now it looks like the pennies are completely silver, so we can take them out. So first off, I got to turn the heat off, and then I'll use my tongs to take them out and just dip them in some distilled water to cool them off. Now that we have some silver pennies, we can take this one step further and turn some of them into gold. So we're going to do this by heating up the penny using my butane burner. As you can see from this animation, the heat helps the zinc atoms migrate into the copper to form brass. The zinc starts as a thin layer sitting on top of the copper. When we add the heat, the atoms vibrate around more, and the zinc can diffuse down into the copper metal. Mixing these two metals together forms an alloy called brass, which is a beautiful golden yellow color. We have to be careful here because we don't want to melt it, and I've done that several times. And then once we've got a nice gold color that doesn't look like it's changing anymore, we're going to dip that into this distilled water to cool it off. So here's our 3 different pennies. Our original shiny copper one that we cleaned in the vinegar solution, we turned it into silver by plating it in zinc, and then we heated that up and turned it into gold by making brass. Now that we've finished with these pennies, what else should I turn into gold? In the last experiment, we saw that metals can have different colors. We saw 2 pure metals, the reddish copper and the silvery zinc, and we saw an alloy, which was the yellow brass. But did you know that almost all pure metals are silvery or gray? There's only a few of them that actually have color. Here are some examples of several interesting metals from my element collection. So copper has a reddish color, gold is yellow, and all of the rest are silvery and gray. But even among those, there are little variations that I think make them all really interesting. Lead, iron, and tin are all varying shades of silvery gray. Osmium and gallium in the middle here have a slight blue tint. Bismuth and vanadium are both crystalline and shiny. Mercury is a beautiful silvery liquid. Silver is a very shiny, almost white metal. And cesium is a silvery golden liquid as well. But why do some metals have color? The color of any object comes from the wavelengths of light that it reflects. So copper absorbs the blue-green part of the visible spectrum, and it reflects orange-red, giving it its coppery color. Gold absorbs blue-green as well, but it also reflects a little bit of the green, which shifts the perceived color a little bit more towards yellow, and you get the golden color. Silver reflects all the colors of the visible spectrum equally, and that makes it look, well, silvery. Have you ever seen one of those cool lava lamps that glows in the dark or sparkles under light? They usually have some weird bubbly particles floating around all inside. But what's inside one of those lamps that makes it look that cool? How about we find out by creating our own lava lamp that doesn't require any heat, using easy-to-find materials at home? So to make our DIY cold lava lamp, here are the materials that you're going to need. Water. I'm going to use distilled water again, but again, you can use whatever kind of water you want. Vegetable oil. I'm using canola oil just because I still have it, but any kind of vegetable oil works fine. Food coloring. I'm going to use red because we're talking about lava here, but you can use whatever color you like. We're going to need Alka-Seltzer, a couple of tablets of this, and some kind of a jar. Doesn't have to have a lid on it, but just something to hold the liquid. We'll start by filling the jar about a quarter full with water. We don't need to be super precise here, just however much you think you want. And then we're going to want to add enough food coloring to make the water very deeply colored. We want it to be nice and dark, so get lots of food coloring in here. And then we'll just swirl it to mix it around and make sure the color looks dark enough. I think that looks all right. Next, we're going to fill the jar most of the rest of the way with vegetable oil. You don't want to go quite all the way to the top because we're going to get some bubbles and we don't want any splashing. Notice how the vegetable oil floats on top and it doesn't mix with the water. That's due to the density and polarity of the liquids that we talked about in the first topic. Remember, we used oil and water there too. The oil is less dense than the water, so it floats on the top. And the oil is non-polar, so it does not mix with the water, which is polar. You could also take this jar and shake it around to watch the layers separate back out, just like we did with the density column. Now when you're ready, grab the Alka-Seltzer and take one tablet and add that to the solution. Now notice when it hits the water, it starts to bubble. And these bubbles are going to carry up blobs of liquid with it. And so it looks just like a lava lamp. Notice that the tablet doesn't react with the oil. It just falls straight through it. That's because the tablet needs to dissolve before the chemicals in it can react together. So they actually don't dissolve in the oil, so it won't react there, and it just falls straight through that layer. But as soon as it hits the water, the reaction begins, and it starts to bubble. As a little bit of extra fun here, after the bubbling stops, you can put the lid back on and tip it on its side, and you get these cool waves in the oil and water. With all these bubbles of colorful water, it looks just like a real lava lamp. Let's cut the lights out and see how it looks then. After doing this several times, the water is eventually going to get saturated with the chemicals from the tablets, and it might not work as well anymore. You can actually recycle the oil layer for a new lamp by just carefully pouring it out of this jar into a new jar, and you can just pour the used colorful water down the drain. Have you ever wondered what causes things like Alka-Seltzer to fizz? Well, it's chemistry, of course. The ingredients that cause this reaction are sodium bicarbonate, which is also known as baking soda, and citric acid, which is found in citrus fruits. This reaction between these two chemicals makes bubbles because baking soda is a base and citric acid is, well, you probably guessed it, an acid. When an acid and a base react together, they neutralize each other to make water, and in this case, carbon dioxide gas. They need water to start reacting though, so the tablet is stable just sitting on a shelf or in the packet, but put it in water and the action begins. What's really neat is that this reaction shows up all over the place. Just about every product you see that fizzes when you put it in water uses this exact same reaction. Any medicine that fizzes, like Airborne or Emergency, and any bath product that fizzes, like a bath bomb or something, they all use the same method to create their bubbles. Take a look at the ingredients the next time you use one and see if you can spot them. What happens when you combine two colorless but toxic solutions? You get golden rain. Well, actually it's a bright yellow solid precipitate, but golden rain sounds so much more cool. This is a demonstration that will involve very toxic solutions, so this is an experiment that should only be done by trained chemists, and I'll get all my PPE ready to go. So here are the two solutions I'm going to use: potassium iodide and lead nitrate. Both of these are clear and colorless, and for this experiment I won't need very much at all to form this golden precipitate. So now that I've got my two solutions prepared in the beakers, you can definitely see they're both clear and colorless and they look just like water. And now I'm going to start by carefully combining these two together. And I'll start by using just a pipette, and we'll do a few drops at a time just so you can see the reaction happen slowly. You can see that instantly a really beautiful gold color forms as soon as the two liquids touch. What's kind of neat here is you can actually swirl this a little bit, and this precipitate is slightly soluble. So you see once you mix it, it all dissolves again. But what happens if we pour all of this one into the larger flask here? Let's check that out. Wow, see you get this awesome gold color. And if the light hits it just right, you can see just these little crystals moving around, and it really, to me, it looks a lot like silk. They're so fine in there, very tiny little sparkly crystals, just beautiful. Now that everything's all mixed together, the next step is to heat this flask to near boiling. Believe it or not, all of these yellow solids are going to dissolve. So I'll just use my hot plate here, set it down on there, and we'll turn it up all the way. So it's going to take quite a while to heat all this up actually, but once it is hot enough, all of this yellow solid is going to dissolve and it's going to look just water clear again, no traces of any solids. So So now that the flask is heated up completely, all the yellow solids have dissolved and it looks just like water again. And so now what we need to do is take this off the heat and let it cool down. And this is going to be a very slow process. The slower the better, actually. So as the flask cools, these yellow solids will begin to reform. And as it cools, the lead iodide grows much larger as thin hexagonal plates. When we did it originally, it formed very quickly, so they're little tiny, tiny crystals and you couldn't really see the shapes of them. If we allow this to cool slowly, you'll get the larger flakes that are much more visible. And it's these golden flakes that float around the liquid that give the experiment its name. In the initial mixing, the solid forms instantly, turning into that yellow milky liquid. Because it reacts so quickly, they appear as tiny little crystals. Now that it's cooling slowly, the solids have much more time to form, and so they'll grow into larger and better formed crystal shapes. That's what makes these thin reflective plates that you see. We can actually repeat this process just by heating the solution again. Each time it's heated to dissolve the solids, it essentially resets the system, and new crystals can grow. But just as it looks cool, it's also extremely toxic. You might have already heard of lead being poisonous, and this solution is just full of it. So I'll need to be very careful when handling it, and I'll make sure to dispose of it properly and safely. Don't try this one at home. To wrap up our segment, we've moved outside, and I'm going to do a large thermite reaction, which is going to result in a lot of fire, smoke, and sparks. So what is a thermite reaction? Well, it's a reaction between metal powders and metal oxide powders. There's actually a large class of reactions that you can call thermites, but the most common one uses aluminum powder and iron oxide powder, which is better known as rust. Since this is a pretty dangerous demonstration, I have to say this is definitely one you should leave to us trained chemists. So I've measured out all of the chemicals that I'll need here, and we've got 225 grams of aluminum powder, really fine aluminum powder, and in this bag is 675 grams of rust. And combined together, this is going to make about 2 pounds of thermite, so it's pretty big. So normally when I'm doing chemistry, I want to keep everything in beakers and nice glassware, but it's a little unwieldy with these amounts, so I'm just going to use a bag here. And that actually seems to work out a lot easier because we can mix these together much easier. Seal it up and then just kind of mix it around like this until we get it all nice and together. What's really interesting about thermite is it's very stable. So it releases a ton of heat once it's ignited, but it also takes a lot of heat to get it going. So we're gonna have to set up an ignition system. So the first step of the ignition system is potassium permanganate, and I'm gonna add that to the little crater at the top of the volcano. Next, we'll add a piece of magnesium ribbon to act as a fuse. And I'm actually gonna use a couple of pieces just to make sure that we have enough. And the idea here is I'm just gonna poke it down through the permanganate in the middle so that it is in the permanganate but then goes down into the thermite as well, so it'll burn like a fuse. The last step is gonna be to add a few drops of glycerin to the permanganate when we're ready, and that will set the whole thing off. So I've taken the thermite over here to this sandy area to set it up, and I've got it on a ring stand suspended over a bucket of sand. And the reason we do this is because this is going to produce a lot of fire and smoke and heat and sparks, and we want to put it somewhere where it's away from anything flammable. So we've got this sandy area, it's far away from any trees or anything, and it's also going to be obviously really hot, so I've got these welding gloves that I'll be using once it's done, and it's going to be really bright too, so I've got these UV safety goggles as well. So now I've got my glycerin, I'll just add a few drops to the pile here, and after a little bit of a delay, it'll start reacting. So that should give me enough time to back away to a safe distance. Perfect. Wow. Perfect. So you can see all the results of the reaction in here. It's a mixture of iron and aluminum oxide. It's still super hot though, but I'm really excited to see how this looks. So I can't wait, and I'm gonna dig it out of here and quench it in some water. It actually, you see the bottom of this has a bunch of sand on it. A lot of that has melted too, so there's a little bit of glass on the bottom. That's how hot it was. So now that this is all cooled down, I really want to see what's inside this. What you can see right now is basically slag. It's aluminum oxide, and it's like a ceramic, so it's really brittle. The iron is a metal, so I'll be able to hit it with a hammer and it will be fine. but we'll be able to break off the aluminum oxide and should see some nice shiny iron, I hope. But let's break it open and see what we see. All right, that was easy. So look at that. We got one solid chunk of iron right in the middle there. So I brought a magnet just to prove that this is iron, since magnets will stick to iron. So let's make sure. Oh, perfect. Ooh, pinch my fingers there. So those are definitely big chunks of iron. So how cool was that? We were able to use chemistry to turn ordinary rust back into iron metal. So this is basically, we're using chemistry, we're using fire and sparks to explosively de-rust an object. So you could use this to fix your wrench or something if it's all rusty, but I don't think the wrench would survive this process. I love chemistry because of all the fascinating reactions and chemical changes. It's just amazing to me that you can start with something like an inconspicuous pile of brown powder and use it to create such an amazing display of sparks and fire and end up with a solid chunk of metal at the end. Chemistry enables us to manipulate the atoms and molecules that make up our world to create new things and exciting reactions. As a scientist, I get to experiment every single day, and you should too. Take a look at the world around you and always be asking questions. Why are things the way they are? Can you think of ways to make them better? How do things react with one another? And then experiment with these questions until you find an answer. There's nothing more satisfying than that feeling of wonder and discovery that comes with using science to explore the world around you. Again, I'm Dan, and I thank you for tuning in to this episode of Sci Notes Chemistry. Stay tuned for Sci Notes Chemistry. Transition to Sci Notes. So, hold on.